2. This is instead of 30, 5 times the time constant is 75, and 75 divided by 15 is that is minus 5. E to the power minus 5. If you do, you will get the correct answer. Can you hear us?
Yes, sir.
Yes, sir.
Yes, sir.
Is this problem clear to you?
Yes,
Yes,
sir.
sir.
How it is done? Very simple problem. This problem is asked in VTU exam once, not with the same data, with a different data, but similar type of a problem. This another problem also appeared in VTU exams once or twice, similar problem, that is this problem. In this problem, there are two things. Just see here. A first order thermometer with 10 seconds time constant is dipped into water bath whose temperature is rising at a rate of 2 degrees centigrade per second. So the temperature of the water bath is not constant. It is rising at the rate of 2 degrees centigrade per second. In 1 second, that means water bath is continuously being heated. So because of that, the temperature of the water is rising at a rate of 2 degrees centigrade. Which type of input is this? If the temperature is continuously increasing with the time, which type of input is this? If the temperature is constant, which type of input is that? That is previous problem. And if the temperature is continuously rising at the constant rate, which type of input is that? It is a ramp input because it is a straight line input. You can see here ramp is shown. The size of the ramp is 2 degrees centigrade per unit time. That is 1 second. Determine the temperature shown by the thermometer after 30 seconds. In that, two parts are given. One, initial temperature of the thermometer and water bath is 20 degrees. Initial temperature of the thermometer and water bath is also 20 degrees centigrade. That means initially the temperature, suppose that is say room temperature. A room temperature is say 20, and on the room temperature, water bath and thermometer both are lying for infinite time. That means if they are lying there for an infinite time, the temperature of both will be identical or same. That is 20. Second case is initial temperature of the thermometer is 20 and water bath temperature is 30. So initially the temperature of the water bath is 30 and temperature of the thermometer is 20. That is the second case. So first let us go for the first case, that initial temperature of the thermometer and water bath both are same. That is 20 degrees centigrade. So initial temperature I have taken. But remaining part, the water bath temperature is continuously rising with the time at 2 degrees centigrade per second. That means it is a ramp signal. So ramp signal equation just now in the previous class we have derived. That is A or K into bracket T minus capital T into bracket 1 minus e to the power minus T by T. Or you can take this minus sign outside. In the previous class exactly what I have done. This is T and minus of minus plus T into e to the power T by T it becomes. Don't get confused. That is the equation we have seen here. See here. This is a ramp signal. This is the equation. K, that I have written it as capital A, T minus T plus T by T. So if I take minus T common here, what remains is 1 minus. This plus line will become minus. That is the only difference. The same equation I have written. Nothing more than that. K I have written it as A, T I have taken minus T common, 1 minus e to the power minus T by T, double bracket complete. So I will substitute the value. Size of the ramp signal, That is the slope of this line. This slope of the line, normally the ramp signal line should start from the origin. But here it is starting at 20. That means the equation of the line is y is equal to mx plus c. M is slope 2 and c is intercept, that is 20. It is indirectly like that. So here you can see this is the output of the system for the ramp input. A is the size of the ramp or K into T minus 10 T into e to the 1 minus e to the power minus T by T. Now the time constant of the thermometer is given as 10 seconds. So capital T is 10 seconds. When you are taking measurement after 30 seconds, after 30 seconds you are taking the measurement, correct? So after 30 seconds means T, small t is 30. I have substituted minus 30 upon 10, minus because e to the power minus is there. So if you solve this, here it will become equal to approximately 41 degrees centigrade. See, remember the temperature is rising at the rate of 2 degrees centigrade per second. In 30 seconds, what is the actual temperature of the water bath? 2 degrees centigrade per second multiplied by 30. That means it is 60 degrees centigrade actually. So the temperature of the water after 30 seconds is 60 degrees centigrade, but the temperature shown by the thermometer is only 41 degrees centigrade. See, there is an error of 19 degrees centigrade. This happens because the first order thermometer continuously lags behind the input. It continuously lags. It will never reach that because there is a constant gap equal to time constant of the system. So 2 degrees centigrade, if you wait for infinite amount of time, there is a 2 degree error equal to time constant, equal to the time constant of the system is 10. So 10 seconds, how much temperature water is rising? In 1 second it is rising by 2 degrees. In 10 seconds it will rise by 20 degrees. So that error will be continuously there. Approximately that much error will be continuously there. So here, see here it is 41. That means there is a 19 degree error is there. So this 41 plus initial temperature of the water bath, that is 20, and thermometer, both are same. So that 20 I have added. So the temperature shown by the thermometer after 30 seconds for this step plus ramp combination, not step, only ramp signal is 61 degrees centigrade. So after 30 seconds, the temperature of the water is initial 20 plus in 30 seconds it will go up by 60, 2 degree per second. That means it is 60 plus 20, 80. 80 degrees centigrade is actual temperature of the water, but the thermometer is showing the reading as 61 degrees. Why this is required is, suppose you are measuring the temperature by the thermometer, this correction has to be applied. Because no thermometer, mercury in glass thermometer or liquid in glass thermometer, for ramp signal will never show the correct reading. Only if the reading is constant, if the temperature is constant, it will approximately show the same reading. But if it is continuously rising with the time, then the thermometer always lags behind that by amount equal to the time constant. That is 10 into, in that 10 seconds, how much is the size of the ramp? If the size of the ramp is 1, then it will it is less by 10. If the size of the ramp is 2, then less by 20. If it is 3, then less by 30 degree, like that. If the time constant is 10 seconds. In the second problem, it is a combination problem. Second part of the problem, B part, if the initial thermometer temperature is 20 degrees centigrade, but the water bath temperature is 30 degrees centigrade. That means, so initial temperature of the thermometer, I have drawn with a flat line 20 degrees centigrade. Initial temperature of the water bath 30 degrees centigrade. So when you dip the thermometer into water bath, first it will be subjected to a step size of 10 degree. So sudden jump of 10 degree, and then it is raising at the rate of 2 degrees centigrade per second. So it is a combination of step signal plus ramp signal. So first initial temperature of the thermometer 20 plus this is the step input. Step input is size of the step is 20 plus 30, 20 to 30. The step size is 30 minus 20, that is 10 into 1 minus e to the power minus t by t. So small t is 30, capital T is 10, minus 30 by 10 is minus 3. So this is the step signal. So, and this is the ramp signal, which is same as this. So 2 into 30 into bracket minus 10 into 1 minus e to the power minus 30 by 10, that is minus 3. So size of the time constant of the thermometer is 10. Size of the ramp signal is 2 degrees centigrade per second. So this plus initial temperature, that is 20 plus 9.5. So even though step size is 10 degrees centigrade, so the temperature shown by the thermometer is only 9.5 degrees centigrade, because here also we have waited for only 30 seconds, not 50 seconds. So the error is 0.5 degrees centigrade in the step and error is 19 degrees in the ramp. So the total reading shown will be 71.5, but the actual reading of after 30 seconds of the water is 30 into 2, that is 60, plus initial 30, that is it is 90 degrees centigrade, but here it will show you 71.5 degree centigrade. So another approximate error of 19 degree centigrade. Is it clear? Is this type of problem is clear? These both problems have appeared in the exam, similar problem. That's why I have taken. These problems will come for around 10 marks, not more than that, 10 to 12 marks. Is it clear?
Yes, sir. Yes, sir.
Then we can go for a second order system. In the first order system, highest power of S in the transfer function is 1. The highest power of S in the transfer function is 0. It is called as zeroth order system. If it is 1, then it is first order system. It may be in denominator or numerator anywhere. So highest power of S in the transfer function, if it is 1, first order. If it is 2, it is second order system. Now a standard second order system transfer function will take and proceed. Since this is our standard second order transfer function. So the standard second order transfer function, you know, spring mass damper system. The spring mass damper system has similar transfer function. That is omega n square divided by s square plus 2 zeta omega n into s plus omega n square. So where omega n is natural frequency of vibration for spring mass damper system or any system. Say any system can be converted into any type of system. Electrical system you can convert it to mechanical, mechanical you can convert it to electrical by using a electrical analogy or something like that. So any second order system transfer function is generally represented by this. C of s upon r of s is equal to omega n square upon s square plus 2 zeta omega n into s plus omega n square. Now you have already studied vibrations, you know this terminology. Omega n stands for natural frequency of vibration in radians per second, whereas zeta is the damping ratio, that is actual damping divided by theoretical damping. So this ratio, if zeta is less than 1, it is called as underdamped system. Zeta is equal to 1, it is called as critically damped system. If zeta is greater than 1, then it is called as overdamped system. All these three types of systems, that is underdamped, critically damped and overdamped systems, are commonly used in a nature. So for example, if you take underdamped system example, your shock absorber of a two-wheeler or a four-wheeler is always a underdamped system. If the damping is less, what happens is the sudden shock is absorbed by the shock absorber and slowly transmitted to the system. So the system oscillations will continue, but the initial sudden force which will be slightly absorbed, and that is what the spring does. But if the in the application of this is you cannot have a very high damping ratio. A high damping ratio means, suppose your bicycle is there. Bicycle doesn't have any shock absorber. I'm not talking about those fancy bicycles which come with the shock absorber now. But I am commonly referring to a common normal bicycle, that black one, age-old bicycle which is commonly used by common man in India. So that bicycle doesn't have any shock absorber. So here it is a rigid frame only. When it is a rigid frame, its damping ratio is very high. So naturally, all the shocks are naturally get transmitted to the person who is riding. Only protection for him is that seat. So seat has a spring, so it acts as some suspension. So it will reduce the shock by using the spring and thereby reducing the damping ratio. Whereas another example, it is overdamped system is also commonly used. Overdamped system example is door closer. If you use the door closer, what is the purpose of using a door closer? If you use a door closer, means to close the door you have to simply use the spring. So if only spring is used, what will happen is the damping ratio is there is no damping. When there is no damping, that means damping ratio is very, very small. That is, friction in the hinges is the only damper. In that case, what will happen is, when you release your hand, the spring will close the door so fast that it will go and hit the frame and create lot of noise, as well as it will damage the frame as well as door also. If it is a glass door, it will get broken also. And at the same time, if any next person is trying to enter, it will go and hit him with a great force. It will cause the accident. To avoid that, we use the hydraulic damper operated door closer. So what is the job of the door closer is, it will increase the damping ratio. So when it increases the damping ratio, the door will close very, very slowly, or practically the door never touches the frame. When it never touches the frame, and hence doesn't create any noise. So when it never crosses, it will touch the frame only when the time t is infinity. So that infinity never comes. So that means the door never touches the frame, and thereby which it will not hit the frame, and so the door is protected this way. But only difference is, it will take a long time to close. There is an adjustment on the damper to adjust, so that you can close the door slightly faster or slightly slower also. That is what you are altering there is damping ratio. If you increase the damping ratio, door will close slowly. If you decrease the damping ratio, the door will close fast. So here, this is what is the terminology. This is the same thing is written in the terms of, this is an open loop system, omega n square divided by s plus 2 zeta omega n, and this is unity feedback system. So overall transfer function is omega n square divided by s square plus 2 zeta omega n s into plus omega n square. So here there are, as I said, there are three possibilities depending on the damping. Damping ratio less than 1, equal to 1, greater than 1. So directly here, see here, this is one example. We'll see the derivation in the next class, and first we'll see the derivation and then see the problems. So the derivation has not been put here. So the derivation we'll see first and then see the example. So we'll stop here today, and in the next class we'll continue. Any questions? Any questions on this?
No, sir.
First order and second order. So we'll stop here.
No, sir. No, sir.